great pleasure to talk today, and yeah, hopefully we are waiting all, I think, for being able to meet in person again also. But this is online formats work also well, I think. Okay, so yeah, I want to talk today about some new results we have with non-invasive brain stimulation, some new protocols and extended protocols, which might be interesting for application basic research, but maybe also in future for clinical studies. So we have different options nowadays to modulate human brain functions. As you all know, we can induce cortical activity with transcranial magnetic stimulation, which induces with one stimulus a short but intensive electrical stimulus at the end, which elicits action potentials in your target area. You're inducing activity, which you need, for example, for diagnostics of neurological patients, nerve conduction velocity, and so on. You can induce plasticity with non-invasive brain stimulation, which means enduring long-lasting alterations of cortical excitability. And here we have a couple of techniques available. We can use repetitive TMS, and here's an example for this kind of plasticity you can see with theta burst stimulation, which is a special version of RTMS, dependent on the specific protocol you use. You can enhance activity, you can enhance excitability of your target area. Here's a motor cortex. So they looked for the amplitude of motor evoked potentials. And you can see that the specific protocol enhances excitability and another protocol reduces excitability. And importantly, as these effects last for longer time after the end of stimulation. You can induce similar effects also with paired associative stimulation, where you combine transcranial magnetic with the peripheral nerve stimulus, and within certain intervals you get also long-term compensation and depression-like plasticity. And you can induce plasticity with tDCS, and this will be the main topic of, or one of the main topics of this talk today. Beyond induction of activity and plasticity, we can also modulate oscillatory brain activity. And the main technique here is transcranial alternating current stimulation, which has been shown to entrain oscillations in the human brain. So a couple of techniques available. We'll start with tDCS. So most of you might know the classical protocol and the principal mechanisms of action. So the acute effects is a subthreshold modulation of resting membrane potentials. You all know that there's a threshold for induction of neuronal action potentials. You can imagine that if you bring the resting membrane potential far away from this threshold, then you need more incoming activity to induce potential. When you depolarize at the subthreshold level, then you need less incoming activity to induce an action potentials. But these are the acute effects during tDCS. And what makes this technique more interesting also for clinical application is that if you stimulate for a longer time, so not for only a few seconds, but here in one of the first studies between 5 and 13 minutes, you can see here again for the model of the human motor cortex that motor evoked potential amplitudes as an index of cortical excitability are enhanced by stimulation with the anode over your target area. And these effects can last for up to 90 to 120 minutes, dependent on the specific protocol you're using. When you stimulate with a cathode over your target area, then you get an excitability diminution, which can also last, dependent on the stimulation duration and intensity, for up to 1 hour after the stimulation. So far, so good. You get neuroplasticity via the stimulation protocol. But there are, of course, a couple of questions associated with these protocols. So do you always get linear effects? So do stronger stimulation, longer stimulation always increase efficiency of stimulation? Do you get always identical effects in different conditions of the brain, of the human, and the stimulation of different areas? And could we maybe even prolong the after effects of the stimulation? Because you can imagine that for clinical application, excitability alteration, which lasts for 1 hour or so, and then the effects are vanished completely, it's not extremely useful in many cases. So To explain strategies for optimizing tDCS effects, we first have to learn a bit about the neurophysiological background. So you all know, I think, about basic mechanisms of plasticity, and one of the important foundations is the involvement of glutamatergic synapses, which can be strengthened or weakened. And if you strengthen them, you talk about long-term potentiation. If you weaken these synaptic connections, you talk about long-term depression. So glutamate is relevantly involved in plasticity, and this works via NMDA receptors, which work as calcium channels. Dependent on the calcium concentration in the postsynaptic neuron, you get strengthening or weakening of synaptic connections via insertion or removal of AMPA receptors to or from the subsynaptic membrane. So if you have high calcium concentrations, there's an insertion of AMPA receptors, which in case of presynaptic activity results in stronger sodium influx, so stronger depolarization of the respective postsynaptic membrane. So this means that the synaptic transmission is strengthened. With low calcium concentration, you get antagonistic effects, removal of these receptors, and the specific synapse is weakened. You have different other substances which are modulating or are involved or gating the effects. So GABA hyperpolarizes, GABA activity hyperpolarizes the subsynaptic neurons, so weakens the efficiency of glutamatergic synapses. And you have different neuromodulators which are involved in the effects of glutamatergic synapses. Dopamine, acetylcholine, serotonin, adrenaline, noradrenaline. We have done a couple of studies there, but if I would start to talk about these, we will sit here for the next hours. But data about the effects of these neuromodulators on synaptic plasticity, especially also with respect to tDCS, are available. So that's a principal mechanism, plus one important principal mechanism of plasticity. And we have shown also in relatively early studies that when we block NMDA receptors, tDCS doesn't induce any plasticity anymore as compared to a sham medication, a placebo medication condition. It's valid for anodal and for cathodal stimulation. And additionally, when we block calcium channels via flunarizine, there's also no plasticity induced by anodal tDCS anymore, which is thought to enhance calcium influx in the postsynaptic neuron. So we can conclude from these data that with tDCS we induce calcium-dependent glutamatergic plasticity. Okay, and I told you already that the specific calcium concentration determines if you weaken synaptic connections, so you induce long-term depression, or you strengthen synaptic connections. And if you think about optimizing the effects, then this dynamics have certain consequences. So as long as you are in the calcium range, which induces long-term depression or long-term potentiation like plasticity, and it should be the case that calcium enhancement results in stronger plasticity effects. And this is what you can see here, that the stimulation intensities between 0.2 and 1 milliamp, the stimulation duration of 5 minutes, you can see with increasing stimulation intensity an increase of the effects of tDCS. And also when you stimulate with 1 milliamp and stimulate for a longer time, you get increasing efficiency of tDCS to induce plasticity. So far it's easy and so far it's linear, but this scheme here with transition zones, no man's lands, and so on, imply also that if you exceed calcium concentration to a certain level, you might activate here for no man's land 2, for example, counter-regulatory mechanisms which reduce calcium influx and then result in other plasticity effects. Katja Montesilva has shown this also some years ago when we conducted a protocol where we prolonged stimulation from 13 minutes to 26 minutes. And she could show here that the 30 minutes anodal stimulation, you get an excitability enhancement, where with 26 minutes stimulation, you get an excitability diminution. We speculated that this is due to exceeding this optimal calcium concentration, getting to counter-regulatory mechanisms, so reducing calcium influx. And we tested this via blocking, again, calcium channels with flunarizine. And you can see here it's this excitability diminishing effect was abolished by gradual block of calcium channels. So this conversion of plasticity effects seem to be also dependent on calcium dynamics. Okay, so when you want to extend the duration and the amplitude of the effects you get, then you have various parameters. You have a large parameter space you can use to optimize the effects. And so you have, and which determines duration of the effects. Also regional is restriction if you think about shaping the electrode size, but also directionality of the effects. And we conducted a couple of studies here, and I will guide you through the most important ones. We probed stimulation durations between 15 and 13 minutes with stimulation intensity between 1 and 3 milliamp. We did also repetitive stimulation because it's known from animal experiments that late phase plasticity lasting for hours or days or even weeks after the end of stimulation are induced by specific repetitive protocols. We did also pharmacological studies. I won't show them here today. And so I want to show you some results here. So first for anodal tDCS, Desmond Aguada did a study where he stimulated between 1 and 3 milliamp for 15 up to 30 minutes. And you can see the results here. Here's the subjects. He took the motor cortex as a model and motor potential amplitudes as a readout for excitability alterations for neuroplasticity. The simple and good news in principle is, I think, that all of the stimulation protocols he showed resulted in an excitability enhancement as compared to baseline excitability and the sham stimulation condition. You can see this here. And what you can also see if you look at the amplitude and the duration of the effects, that 3 milliamp stimulation in all stimulation conditions resulted in larger and more stable effects as compared to 1 and 2 milliamp stimulation. Besides, if you want to do this, we combine this with topical anesthesia, because if you stimulate also with relatively large electrodes, we use in this experiment with 3 milliamperes. Otherwise, your subjects will perceive relatively prominent tingling and itching sensation, and we of course wanted subjects to be blinded. So with 3 milliamp you get gradually better effects. So what he did then in the second study was to compare the effects of a single stimulation condition with repeated stimulation with 20 minutes interval and 3 hours interval. And we use these intervals because we know from previous study that repetition with short intervals, so 20 minutes, induces late phase plasticity, whereas longer interval stimulation with 3 hours interval doesn't induce these late phase effects, which last for more than 1-2 hours or so. So we compared these effects, and you see that with the 1 milliamp 15 minute stimulation, and also with intensified stimulation with 3 milliamp, you get excitability enhancements with one stimulation session lasting for about 30 minutes after the end of stimulation. But if we do the repetitive stimulation with short intervals, you can see longer lasting effects in both conditions, but late phase effects, which lasted up to the next day, were only present in the lower intensity condition, whereas with the high intensity condition, the effects were relatively shorter lasting. If you have longer intervals, you can see trend-wise antagonistic effects of the stronger stimulation protocol. This is something we saw also in previous studies already, and a partial restitution of plasticity effects with a weaker protocol. So this means, in principle, we can induce late phase plasticity with our stimulation, with repetitive stimulation within short intervals, but there's a non-linear dependency on stimulation intensity. So here weaker stimulation with 1 milliamp has better effects with regard to this long-term plasticity, as late phase long-term plasticity as compared to stronger protocols. And Mosayevi did the parallel studies with the cathode electrode over the primary motor cortex, which in principle reduces cortical excitability. Same stimulation protocol, stimulation intensity between 1 and 3 milliamps, stimulation duration between 15 and 20 minutes. And the effects differ here from those of anodal stimulation, not only as expected with regard to the directionality, but also with respect to the directionality, to the stimulation intensity dependency. You can see that with 1 milliamp stimulation and with 3 milliamp stimulation, you get an excitability diminution. Whereas with 2 milliamp stimulation, you get an excitability enhancement, especially with the 20-minute stimulation protocol. So you get a switch of the direction of plasticity. And this is also something which was known. This is intensity dependent so that with 2 milliamp, you get an excitability enhancement if you stimulate for longer than 5 or 10 minutes. The reason might be that this more intensive stimulation enhances calcium concentration to a level which induces long-term potentiation. Question is, of course, then why do we get this inhibition again with 3 milliamp? And our idea was that you might then be in the calcium overflow range, activating counter-regulatory mechanisms, or what we saw also with anodal tDCS. And we tested this via gradually blocking calcium influx with different dosages here of flunarizine. You can see indeed with 3 milliamp stimulation, with the lowest dosage, you don't get a shift of this excitability diminution, but with the highest dosages, the effects switch under calcium block into an excitability enhancement. So that's in favor for indeed a calcium overflow effect with this 3 milliamp stimulation. It might be also the case that stronger stimulation, of course, causes relevant effect also in deeper areas. So there might be a mix of different effects inducing this secondary inhibitory or excitability diminishing effect. Mosen then also did this repetitive stimulation with short and with long intervals. So principal protocol the same as with anodal stimulation. You can see here that we get this excitability diminishing effect with 1 and 3 milliamp. And that the effect might, but the effect is not really relevantly prolonged via repetition with second stimulation condition. As you can see for the short intervals, also for the long intervals. For the long intervals, we have a kind of reduction of the after effects. This has been also shown in studies before. But might be the reason why we don't get here long-lasting plasticity might be that LTD might be a bit more tricky to induce for late phase plasticity. That's known also for animal experiments, where their standard protocol is involving more than one repetition to induce this late phase plasticity. So for cathodic stimulation, repetition is not the key in the way we did it so far for inducing late phase plasticity. So I've shown you so far that dosage-dependent effects are not linear in each case. And extending tDCS beyond 1 milliamp and 15-minute stimulation, so which is kind of a standard for basic studies, can however gradually improve efficiency. And repetition of stimulation within specific intervals induces late phase plasticity for anodal, but not for cathodic tDCS. Okay, so you get gradual improvement and gradual optimizing effects via modification of the stimulation parameters. Most of the basic studies have been conducted so far in the primary motor cortex, but if you think about applications, then of course other areas are more relevant. And the question is, do the effects we see in the motor cortex transfer to other regions? And the simple answer is gradually, at least. So for visual cortex stimulation, that's a study conducted by Andrea Antal. She showed also excitability enhancing effects on the N70 amplitudes of visual evoked potentials of anodal tDCS, reducing effects of cathodal tDCS. But as you can see here, for seeing an excitability enhancement, we have to stimulate longer, and the after effects are shorter as compared to after effects achieved in the elicited in the primary motor cortex. Cathodal stimulation that seems to be a bit easier to induce this plasticity and also a bit longer lasting. So you might have to intensify protocols to get really good effect at the visual cortex. For the somatosensory cortex, anodal tDCS works nicely on somatosensory evoked potentials, as you can see here. whereas cathode stimulation didn't have an effect in this study on the resting somatosensory cortex, since we are modulating cortical excitability and activity. And in the specific conditions we have here, you're sitting for a relatively long time without moving and so on, you don't have much somatosensory input. Well, this might be the reason why we didn't see here effect of cathode tES. We saw effects on some basic somatosensory functions in other studies, however. So you can see here also that transferability seems to be a bit gradual. Prefrontal cortex is an important area involved in many neurologic and also psychiatric diseases. So we were interested if the primary motor cortex effects transfer to the prefrontal cortex. Did here also one study for cathode stimulation, another study for anodal stimulation, and measured excitability alterations with TMS-EEG. So in this protocol, you evoke cortical activity with TMS, and you obtain respective excitability data, and then was resulting evoked potentials in the EEG. So I think you don't have to understand each detail here, but that's principle how it works. And so we measured in this protocol, we obtained data from the primary motor cortex and also from the prefrontal cortex, looked for effects, looked for TP amplitudes before and after stimulation. And so you can see here, these are these cortical evoked potentials. You have early waves, you have later waves, which have different meaning. For anodal tDCS, when we looked at the MEPs, we saw for low dosage stimulations 1 milliamp and high dosage with 3 milliamp, that we saw respective excitability enhancement, also compared to a sham stimulation condition. And for the cortical evoked potentials, we saw, this is here the primary motor cortex, very similar or directionally similar effects to what we saw with the MEP amplitudes. Here for the early wave P30, which depends on the glutamatergic system, there's an enhancement of motor cortex excitability. We saw very similar effects also for prefrontal excitability, so also here an enhancement of this early glutamatergic wave. We saw a reduction of the N45, which is primarily controlled by GABA, especially with the high dosage of stimulation, and also with the low dosage in case of prefrontal stimulation. The effects last also for a certain while after stimulation. And for the later waves, you see relatively minor effects. P60 is controlled by glutamate and GABA, so slight enhancement here. For the N100, which can be, however, also affected via somatosensory stimulation, we saw relatively minor effects, but relatively stable effects here. So this might be mostly due to the auditory stimulus in the seasons with primary motor, but not with prefrontal stimulation. And of course, with primary motor cortex stimulation, the coil is nearer to the ear, so this might explain these effects. So the effects here are relatively well comparable and also intensity dependent. Mosaievi did the same study for cathode stimulation, so same protocol. Also here you can see this is 1, 2, and 3 milliamp. You can see with 1 and 3 milliamp excitability reduction with the MEPs, enhancement with 2 milliamp stimulation, and we saw largely antagonistic effects of cathode stimulation also on as compared to anodal stimulation, also on the TEPs obtained over the motor and prefrontal cortex. Interestingly, you can see here it's primary motor cortex stimulation also for the TEPs, an intensity dependent effect. 2 milliamp stimulation enhances excitability here, but this effect is restricted to primary motor cortex. If you look at prefrontal stimulation, this is a 4-electrode position. You can see with all stimulation intensities, you get an excitability enhancement. You get here relatively minor effects with N45, with this mixed P60. You see here also a reduction of cortical excitability and roughly no effect on the N100, with the exception of this minor effect here, which shows an activity enhancement. So in principle, for M1, MEP, and TEP, after effects are comparable for M1. So that's good news because you have stability here. Those M1 effects are principally transferable also to prefrontal areas. effects its prefrontal areas might be gradually smaller with the same stimulation intensities. This might be due to electrical fields, which are smaller and with prefrontal stimulation with the same intensities, but also other electrode configuration regions. And we have in prefrontal areas, we see no nonlinear effects of cathode tCS with the given dosages. So that's practically an important information if you think of stimulation in depression, where you do often bipolar stimulation, anode left, cathode right, often with 2 milliamp. And there was always a discussion if cathode stimulation with 2 milliamp over prefrontal cortex results also in unwanted, in this case, unwanted excitability enhancement. It seems not to be the case. Okay, then the next question is if we can transfer these effects also to other areas. Do we have the same effects also in different groups of individuals, or are there modulatory effects of different brain states and different factors? And if I ask this question, you might imagine that there are differences. I want to show you two examples. One important example is higher age. Nitsche, Kashemi, and Shervan conducted a study in different age groups where she looked at the effects of 1 million 15 minutes anodal and cathode tDCS. And you see that young subjects showed relatively nice plasticity and asking for about 1 hour after the end of stimulation with this protocol. For young elderly subjects, which in our groups were between 55 and 65 years, you can see here that there's a gradual decline and with the stimulation intensities. With old subjects over 65 years old, you don't see any effects of anodal tDCS. It's quite similar to what you see in animal experiments, where there's a higher threshold of LTP induction with higher age. You don't see also in accordance with animal experiments, we don't see an age-dependent effect of LTD induction via cathode tDCS, and that's a sham condition where you see that subjects without any stimulation were quite stable. So there's this decline of anodal stimulation effects. And we asked if we can induce, however, plasticity also in older subjects with enhancing stimulation intensity. And you can see here, so we had a younger old group and we had an older old group. You can see that with all stimulation intensities we used here, we got excitability enhancement. And also here, as I showed before in the young group, in the older group, also in the older groups, stimulation with 3 milliamp in both older groups evoked more stable effects on motor cortex plasticity as lower intensity stimulation. So the higher threshold for induction of LTP does not mean that at a higher age you don't have LTP anymore. A second factor which might modulate plasticity induction via tDCS, it's chronotype. So you know that that's a different type of different kinds of people. So some are very awake and very happy to get up in the morning, and some are more happy to party longer, but to get later up in the morning. So you have early and late chronotypes, and it's known that cognitive performance in these chronotypes depend on daytime. Early people are better in the morning, late people are better in the afternoon, or it's the daytime at later hours. Ali Saleh-Nejad did a relatively complex studies where we looked for cortical excitability, plasticity, different cognitive parameters, early and late chronotypes dependent on the daytime of performance. And I want to show you, guide you not through the whole studies, but through single aspects here. With respect to plasticity and motor learning, which is known to depend on plasticity. And what you can see here is that for early chronotypes, when we measure plasticity at 8 o'clock, 9 o'clock in the morning, they had relatively prominent LTP-like and LTD-like plasticity. And we measured the same protocols in the evening at 7 p.m. in these subjects, they had a reduced plasticity. This was completely different in late chronotypes. They had a better plasticity of ATP-like and LTD-like plasticity in the late hours of the day and reduced plasticity in the early hours of the day. Also had a sham stimulation condition. You see this here as well. Interestingly, this was associated also with different motor learning performance. So in the early chronotype, as you might expect now, they have better learning performance in the morning at 9 o'clock in the morning as compared to the evening at 7 o'clock in the evening. We used here sequence motor learning tasks and reduced reaction time show better performance in the sequences. That's a random control condition to look for specificity of the effects. And you see here a clear difference. And you see an antagonistic difference in late chronotypes. They are doing significantly worse in the morning as compared to the evening. So chronotype might be an important factor which determines your direction of plasticity. If you think about clinical application, again, this might be relevant when you think about when, for example, you do your therapeutic sessions with occupational therapy or related things. People should relearn motor functions and maybe also other functions. And then it might be, if possible, also good to take into account chronotype. Okay. So individual characteristics affect plasticity response to tDCS. Higher age reduces ATP-like plasticity, but not LTD-like plasticity. Plasticity can, however, still be induced by tDCS in higher age. And what I've shown you too is that chronotype determines the size of plasticity response and the amount of learning at specific day times. So something to take into account if you plan your studies also. So I will use the last minutes now for tACS. So the main function or the main function tACS is used for is to alter oscillatory brain activity. So it's also subthreshold stimulation method. You don't induce respective activity, but you modulate it. So if there's no activity in a certain frequency range, you won't induce it. But you can modulate, enhance, for example, if you align stimulation with your brain activity, you can modulate respective activity. This has been shown in a couple of studies here, for example, Helfrich and colleagues. They identified the individual alpha frequency of their subjects. Then they conducted tACS in this alpha frequency range. You can see here that under real stimulation conditions, there's enhancement of alpha activity, which was stable for about 1 hour, whereas under sham stimulation, there was also an increase because subjects are sitting there, do nothing, so this increases alpha activity naturally, but this increase was much lower. This shows that you entrain this activity, and Kanai and colleagues showed in a visual cortex stimulation study that the effects of tACS depends on the level of spontaneous activity. When eyes were open, they did visual stimulation. They looked for phosphine thresholds, so the TMS intensity you need to induce a phosphine, and this was largely reduced via stimulation in the beta frequency range, which dominates under light and eyes open conditions, whereas when the environment was dark and eyes were closed, an alpha frequency stimulation, but not beta frequency, reduced phosphine thresholds, so enhanced excitability at the end. Well, this shows that the effects of tDCS really critically depends on the predominating frequency in your target area. We conducted a study which was published 2 years ago in our laboratory, which was conducted by Miles Wisniewski, where we looked for effects of beta frequency stimulation in the motor cortex. We were interested in the oscillatory effects, but also in effects on neuroplasticity, which we obtained with TMS over this area. And we were also interested in mechanisms, thought there might be a dependency on the glutamatergic system, so we blocked glutamatergic activity in specific branches of the experiments with dextromethorphan. And so what we showed is that you get an enhancement of oscillatory activity with 20 minutes 2 milliamp stimulation, which lasts for about 60 minutes after the end of stimulation. With dextromethorphan, there was a complete abolishment of this enhanced oscillatory activity. And this was not only local, but we saw also enhanced connectivity between the primary motor cortex and the posterior parietal cortex, which had a similar temporal dynamics as compared to the oscillatory, to the regional oscillatory effects. And also these effects were abolished by glutamatergic block. We saw also an induction of plasticity lasting for more or less identical time course as long as we measured, which was also dependent on the glutamatergic system. So we can alter oscillations via prolonged tACS. I've shown also that there's a frequency specificity of these effects. We enhance synchronization with neighbored areas. In this study, we had relatively regional effects. We use small electrodes here. We have not only effects on oscillations, but also neuroplastic effects. And these effects depend on NMDA receptors. One limitation of the effects of tACS is, however, as I already outlined, that you can't induce oscillatory activity. So you can modulate this activity. This can last relatively long. But if you don't have an activity in a specific frequency, you won't induce it. This makes this kind of stimulation sometimes a bit inconvenient, and it might mean that you have to individualize the frequency you're stimulating with. And we look for a way out here by combining tACS with rTMS. It's known that with rTMS you can induce oscillatory activity, but these activity don't last very long. So we thought when we combine rTMS of a specific frequency with tACS, we can induce this frequency in the brain via rTMS, and then we can stabilize these effects with tACS. This study was conducted by Tiam Hosseinian and by Asif Yamir. This was in the former EU Illuminous project where also Aurora was involved. And we did here bilateral prefrontal stimulation, combined TMS with tACS, and applied the TMS parts at the peak, the TMS parts of the peak of the sinusoidal wave induced by tACS. Had, of course, different conditions, stimulated at the peak to enhance efficiency, tACS, rTMS alone, Shem rTMS and Shem tACS, and we stimulated another control condition also in the through of the tACS induced sine waves. What we indeed got, as you can see here at figure B, is that with this kind of stimulation, so TMS given at the peak of the tACS induced sine wave, you can see that there's enhancement of alpha frequency in the 10 Hertz frequency, which lasts for at least about 30 minutes after the end of stimulation. You see this when subjects have their eyes open, also when their eyes are closed. And when you compare this with the other conditions, these effects are significantly stronger as compared to tACS alone, rTMS alone, and also when you apply the TMS stimulus at the through, and of course when you do sham stimulation. So there's indeed superior effects on oscillatory activity, and these effects has this last for at least up to 30 minutes after the end of stimulation. We have shown also that these effects are not regionally restricted. We have the strongest effect here in the prefrontal cortex where we stimulated, but have also effects at parietal regions, so more posterior regions. You see this when we contrast the effects with baseline, but also when we contrast these effects with sham stimulation. It looks a bit weaker there, but the pattern is still very similar. And these effects are primarily present when you combine rTMS with tACS at the peak. So we have shown this for alpha frequency. We showed this also for theta frequency. This is more or less the same stimulation protocol. So we combined tACS with rTMS in the theta frequency range. So the results look also pretty similar. You get the best effects in oscillatory activity with these combined protocols. So we did 6 Hertz stimulation. This is under eyes open and eyes closed conditions. The effects had a similar duration also. The important additional study we did here is that it's known that theta activity is important for working memory performance. So we let our subjects conduct the working memory tasks, and letter-back task before and after the stimulation, N-back, which is relatively simple, where we did see an effect, and then we let them do the 3-back task. And what you can see here also is that there are some effects with RTMS, with no effect with RTMS only, but there were some effects with tACS only. tACS has been shown to affect working memory when applied in this way, but you see also it's a gradually larger effect with this combined stimulation protocol. So this combination of tACS and RTMS has functional relevance also. Okay, so I've shown you here that we can induce long-lasting effects of tACS on beta frequencies. These are accompanied by plasticity and NMDA receptor dependent, and are NMDA receptor dependent. I've shown you also that combination of RTMS with tACS induces and stabilizes oscillatory activity, and that this combined stimulation has functional value. Okay, so putting everything together, systematic dosing of stimulation parameters revealed partial superior effects of intensified tDCS protocols. Individual characteristics such as age and chronotype affect plasticity response, so this is something to keep in mind, I think, also for application. And advanced tACS protocols allow the induction of long-lasting after effects, which are functionally relevant. That's more or less all I had to say, and these are the people who are conducting the work in the laboratory. So many thanks for your attention, and I think now it's time for questions.